this episode. Today, we're diving into something pretty fascinating. The tiny forces that play a big role in microelectromechanical systems, or MEMS.
Yeah, MEMS. Those tiny machines, often just a few micrometers in size, right? Like the sensors in your phone or those little switches in electronics.
Exactly. And what's wild is that at these tiny scales, forces that we never really notice in everyday life suddenly become huge players. One big problem is something called stiction, when parts stick together permanently and cause the device to fail.
Right, and today we're looking at a study that explores how a quantum force, the Casimir force, combined with surface roughness, affects how these MEMS devices behave and how reliable they are.
So, let's start with the Casimir force. It's a bit of a mind bender. Even empty space isn't really empty. It's filled with tiny electromagnetic fluctuations, kind of like a restless sea of energy.
Yeah, and these fluctuations create a force that pulls neutral objects together when they're extremely close, usually below about 100 nanometers. That's less than 1,000th the width of a human hair.
And unlike electrostatic forces, which you can switch on or off by applying a voltage, the Casimir force is always there. It's like a constant background pull.
Which means in MEMS, where parts are separated by these tiny gaps, the Casimir force can cause parts to snap together, leading to that dreaded stiction.
Now, you might think surface roughness. Those tiny bumps and peaks on surfaces would just make things worse, right? Like causing unpredictable contact or wear.
That's what I thought too. But this study shows a surprising twist. It turns out that roughness influences both the Casimir and electrostatic forces in some pretty complex ways.
The key is those rare, very high peaks on the surface, called asperities. They're statistically rare but can bring surfaces much closer locally than the average roughness suggests.
Exactly. These rare peaks dominate the interaction at very small separations and really affect the forces. Plus, roughness shifts the minimum possible distance between surfaces from 0 to a finite value, what they call the contact distance.
Which is important because it prevents the forces from becoming infinitely large. So roughness actually puts a kind of limit on how close surfaces can get.
That's pretty interesting. So in a MEMS device, you have a moving part suspended by a tiny spring, kind of like a miniature seesaw or diving board.
Right, and when you apply a voltage, electrostatic forces pull the parts together. The Casimir force adds to that attraction and can't be turned off. Meanwhile, the spring tries to push the moving part back to its original position.
So the balance between these forces, Casimir, electrostatic, and the spring, determines whether the device moves smoothly or ends up stuck.
Now, the study talks about equilibrium points, positions where all these forces balance out. If the spring is strong enough, the device can oscillate around a stable equilibrium, like a swing going back and forth.
But if the spring is too weak, the device can suddenly snap to the other surface. That's stiction. This sudden change is called a bifurcation, a tipping point where stable and unstable equilibrium merge and disappear.
And here's where roughness plays a role again. Rougher surfaces require stronger springs to maintain stability. But at the same time, roughness prevents surfaces from getting too close, which reduces the maximum force and lowers the risk of stiction.
So it's a bit of a trade-off. Roughness brings stable and unstable equilibrium points closer together, making the system more sensitive, but it also keeps surfaces apart enough to limit the forces.
Another neat insight from the study is that the Casimir force at separations below 100 nanometers is roughly equivalent to applying a small voltage between about 0.2 and 0.6 volts.
That's a great way to think about it. Like a constant background pull similar to an electrostatic force. It helps engineers compare this quantum effect to something more familiar.
So perfect flat surfaces might seem ideal, but they can actually lead to stronger forces and a higher risk of stiction.
And very rough surfaces need stronger springs to keep things stable. The sweet spot is probably somewhere in between. Moderate roughness that balances these effects.
The authors also point out that their analysis assumes ideal springs following Hooke's law and no friction, which isn't always the case in real devices.
Yeah, real MEMS might have nonlinear spring behavior and frictional forces, especially when operating in air. Interestingly, roughness might help reduce nonlinear oscillations by limiting large movements.
So future studies will look into these effects to better understand and improve MEMS reliability.
To sum up, tiny quantum forces like the Casimir force really matter in MEMS. And surface roughness, often seen as a problem, can actually help prevent parts from sticking by keeping surfaces apart.
Designing MEMS is all about balancing these forces, quantum, electrostatic, and mechanical, to build reliable tiny machines that power so much of our technology today.
Yeah, it's amazing how something so small can be so complex. Makes you appreciate the engineering behind the scenes.
Absolutely. Well, thanks for joining me to unpack this fascinating topic.
Thanks. It was great to explore this with you. Until next time.